Welcome back to part 2 of this chapter. One of the challenges of NMR is that we start by observing a free induction decay such as this, and that the human eye is not well equipped to perceive the frequencies that are contained in the signal. And therefore one needs a transformation from the time domain signal that we have here into a frequency domain signal that we immediately recognize, in this case a quartet. And it turns out that the transformation to go from the free induction decay to the spectrum is known as a Fourier transformation, which we write like this. And let me try to explain how this really works. First of all, we have a signal which could be something like this. S of t is the initial amplitude, in this case we consider a real signal, times cos omega t. So the raw signal that comes out of the spectrometer looks like a cosine wave. Now the first step of the Fourier transform consists in multiplying this S of t with an artificial cosine wave that we can call omega test times t. And this of course will be the product of the initial function times the new function. And if these two frequencies, the actual resonance frequency and the test frequency, are different, then we have a beat pattern. So in this case, omega test is different from omega, the frequency. But if they are equal, then of course the net effect is that we have a cos square. So this is the case where test is equal to omega. And in that case, we see that we have a square of a cosine function. Now the difference is that in this case, if we integrate over all of these values, then we get 0 or something that will converge to 0. Whereas if we integrate over a positive function, it will be non-zero. So in this case, we have a resonance when omega test is equal to omega. So the idea now is to take the raw function and vary this omega test systematically. So omega test could be something like n times delta omega test. So this would be the increment here, and n would be a number of steps, n going from 0 to 1 to 2 all the way to n minus 1. And at each value of n we do this operation again, and when they are different, when omega test is different from omega, we plot something that is 0, so omega running from left to right in this case. There is no effect here at all, except maybe some noise, and then suddenly we hit a condition where omega test is equal to omega, in this case called omega 0, and we have a peak with an amplitude a, and if the omega test function goes beyond the resonance frequency, it becomes 0 again. So this in a nutshell is what the Fourier transform is all about, and it turns out that we can define the spectrum in frequency domain as the integral of the spectrum of the signal in time domain times cos omega test t, brackets like this, integrated from 0 to infinity. So this is a simple way of looking at the Fourier transform. You can also do this simultaneously for the cosine and the sine component, in which case you need a complex Fourier transform, which is indeed what modern spectrometers use. Now once the Fourier transform is understood, you can use it to analyze signals. So this nice beat pattern actually corresponds to a proper binomial quadruplet. This more complicated pattern actually corresponds to some arbitrary distribution of chemical shifts, and it would be very hard to recognize by eyeball what the frequencies are that are contained in the time domain signal, and that is why the Fourier transform in this case is essential to make the information readable to the human. Fourier transformation make it very simple to do signal averaging, although signal averaging has really nothing to do with Fourier transforms. Let me first explain what this is all about. It turns out that if we record the same quadruplet 4 times, then the signal will be essentially the same from one scan to the next, but the noise will be different. The noise is stochastic. If we then add up the 4, the signal will be 4 times as intense as of the individual components, whereas the noise will be in proportion to the square root of the number of records that we have added together. So in this case, if we take 4 different noise traces, then the square root of 4 is equal to 2, and therefore the noise level only increases by a factor 2. Now it turns out that in Fourier transform NMR we use this all the time because we apply pulses, observe the free induction decay, apply a new pulse, a new free induction decay, etc. Sometimes hundreds or even thousands of times, and that allows us to benefit from this advantage. But you can do the same in the old days of continuous wave NMR, and you can do it in virtually any form of spectroscopy, and this is well known to all people who observe signals that are very weak, such as routinely the case in astrophysics. Now there are a number of important experiments. First of all, there are experiments that have been designed for the measurement of T1, that is the longitudinal or spin lattice relaxation time, and this experiment is known as inversion recovery. So in inversion recovery, we apply a 180-degree pulse to the magnetization so that it turns upside down. And then we wait a variable delay tau, which can be varying from milliseconds to seconds, whatever the case may be useful, and before we apply another 90-degree pulse and observe the signal. Note that after the 180 there is no transverse component, so there is no precessing magnetization. Now, depending on the duration of tau, tau 1, tau 2, tau 3, the longitudinal magnetization may be still upside down and somewhat shorter. It may then almost converge to zero. It may already have become positive, or it may have completely recovered to its equilibrium position. Whatever the case may be, the subsequent 90-degree pulse will rotate this magnetization from its position towards the minus z-axis into the plus y-axis, or if it has already recovered, from the positive z-axis to the minus y-axis. And consequently, the signals will be negative up to the 0-point crossing and then become positive. And it turns out, as we know from the relaxation chapter, that this will converge to an asymptotic value, which is the equilibrium position of the magnetization. And the curve that we see here is simply given by the exponential, so the deviation here, this deviation delta, is given by delta, its original value, times e to the minus t over t1. Mind you, this experiment also works if the initial inversion is not perfect. It could be that the negative component is a bit shorter than the positive component, and therefore we would perhaps not start at -1, but we would have a slightly different decay, but we can still measure the deviation accurately. The only point is that we have to introduce a variable fudge parameter here in such cases, which are quite commonly encountered. Inversion recovery is a very rewarding experiment because it's easy to do and it gives you immediate insight into the relaxation of the different sites. So here we're looking at the different protons in this dinitrobenzene, and you can immediately see that some of them recover very quickly. For example, the H5 proton, which is here, which is actually squeezed between the H4 and the H6 protons, and therefore it benefits from rather strong dipole-dipole couplings. And as a result, it recovers very rapidly. You see the zero passage is already achieved after a few seconds. H4 and H6 are less lucky. Both of them have just one dipolar coupled partner, and consequently the zero passage is somewhat delayed and the recovery here is slower. And finally, H2 is kind of isolated out here. It has no immediate proton neighbor, and consequently its zero passage is even further delayed. Now, of course, these pictures can be recorded, and in fact they can be interpreted as follows. One of them goes very rapidly, another one goes slower, and the third one goes very slowly. So this would be as a function of tau. This is the equilibrium magnetization, and you can always extract different relaxation times T1 from these different recovery curves. Now, if we are concerned with the measurement of T2s, that is to say transverse relaxation times, also known as spin-spin relaxation times, then we have to learn how to do spin echoes. Spin echoes were invented in the 50s by Erwin Hahn, initially by accident. This is known as a serendipitous invention. And the idea here is that instead of doing like inversion recovery, a 180 first and then a 90, here we start with a 90 in order to generate transverse magnetization, and we then apply a 180. Now remember that the signal has decayed here, partly because of its natural true transverse relaxation time T2, but partly also because there is a distribution of resonance frequencies due to the inhomogeneity of the magnetic field. And it turns out that this decay, the inhomogeneous decay, can be reversed, and in fact this reversal leads to an increase of a signal, the formation of an echo, followed by the natural decay of the signal again due to inhomogeneous distribution. So how does this work? Well, the first thing to do is to take magnetization in its equilibrium position. We then rotate this through 90 degrees about the x-axis so that it ends up along the minus y-axis here. And then, depending on where we are in the sample, some magnetofactors may rotate slowly, others a bit faster, and others are in a great hurry and will be far ahead because they are experiencing a larger frequency. Then we apply a 180-degree pulse around the y-axis, so that would be like this. And as Erwin Hahn would have said, amounts to flipping the pancake. So the entire picture is simply reversed by symmetry, by a plane of symmetry along the z0 y-axis. So the C vector ends up behind here, and so does the B and the A. But they continue to rotate at their specific speeds, so that it turns out that, and always they continue to rotate counterclockwise, so it turns out that the path described by A here is exactly the same as the path described by A in the defocusing period. B in the refocusing period will have a longer path, but it also had a longer path in the defocusing period, and C has the longest of all, which corresponds to the large excursion. And when tau, the refocusing period, is precisely matched with the duration of the defocusing period, then all three vectors end up along the same axis. That means the interference between these two vectors is constructive, and that means that the signal will be intense. And it turns out that we can extract a T2 from this by comparing the signal here, which is the signal at the time of the echo, and comparing it with the signal here, which is at the beginning of the experiment, and we notice that this decays as a function of 2 tau, which is the overall time between excitation and echo, divided by T2. Now, to understand how this echo forms, it may be convenient to draw a diagram of the phase as a function of time of these three components. Let's start with component A. So during the defocusing period, it starts with a phase 0 and it builds up a phase, which is what we see here. Because of the refocusing pulse, the phase suddenly changes sign from phi to minus phi, and that corresponds to the reversal of this sign here to the opposite position. And then during the refocusing period, it will converge and come back to a vanishing phase. So this would be for A. In fact, the slope is nothing else but the frequency of A. We can do the same thing for the component B, which, as we have seen, precesses faster and therefore builds up a phase difference more faster, and this will be reflected into a symmetrical position and then continue its precession in the refocusing period and precisely catch up with A at that point. And component C is even more dramatic. C will diverge more rapidly, refocus here and C, and all three components should end up at the same time, at the same phase, at the time of the echo. This concludes part 2 of this chapter. Thank you for your attention.